Hello everyone, I am welcoming you all once again to this channel. So today I am going to make a video on the VASP tutorial. So from earlier video in the earlier videos we have seen how to calculate the self consistency field, next how to do the lattice optimization, then some van der Waals correction. So all these kind of different videos we have already seen, and today I am going to make a video on how to make any constraint dynamics. Like if you must have heard about the selective dynamics. If you want selectively do the dynamics by fixing some other atoms and by setting some other atoms for moving, so this way how to modify our structure, how to write the POSCAR file, so that thing we will see today. So let's first see what kind of structure I have taken. So here I am going to open the POSCAR file using our VESTA software first to show that which structure I have taken. So as you can see here, I have taken this kind of a layer where we are having three atoms. This sky color one is titanium, and this oxygen is this red color is oxygen, and the black color one is carbon. So this is nothing but a Ti3C2O2 layer. Okay, so this is a magazine, and these oxygens at the termination, and Ti are the metal atom, and this is the carbon. Okay, so this way I have taken the structure, and this is the structure of a supercell. As you can see that we are not having only Ti3C2O2. That means we are not having only 7 atoms, rather we are having at 63 atoms. So this is a 3 by 3 layer of the magazine unit cell. So now this is a supercell. Okay, so here before going to show how to do the selective dynamics, I will also try to show how to do normal dynamics or normal optimization first, then we will do the optimization using certain constraint. Okay, so let's start. So here I will open first the POSCAR file. So see here that this is our Ti3C2O2, but the supercell of that, and this is the cell parameter. Like you know that this is A and this is B1, which is A cos theta B sin theta, like that you know, and this is the C value, and which is also included certain vacuum along it. Okay, and this is the Ti, and you as I told that this is a 3 by 3 layer, and in the unit cell we usually have Ti3 C2 and O2. So 3 by 3 is 9, so 9 cross 3 is 27, and that way 18 18. Okay, so this way the atoms are arranged in the POSCAR file. So also I will try to show you how the incar for the same is written over here. So the incar, these are the normal optimization, as you know, and here I have not taken the spin polarized calculation because titanium is kind of non-magnetic, or you can say that the up spin and down spin in Ti is kind of is they are cancelling each other. So that means if we will ignore the same for Ti only, so that is also fine. Okay, and these are the all the normal lattice optimization parameters that I have used, and here also I have used the van der Waals correction part. Okay, and this is, you know, that when sometimes we get some difficulty in optimizing, we can use also this mixing parameter like A mix, B mix and all. Okay, so no simple optimization file we have taken, and next part is to show the k points. So here the k points, as I have told that this is a supercell. So in the unit cell I have taken I think 15 15 1 I think. So in that way you can decrease, or you have to decrease, because as we are going farther in the real space, we need to reduce our k point in the reciprocal space. So that way I have taken here 331. You can also take 551, but it will take more time, but it will provide you even accurate result. And next part is to see the POSCAR. So the POSCAR, there is nothing to see over here. Still I am showing that you see that it's a very big file. So for quantitative analysis you can do this grep title POSCAR. So see here we are having titanium, carbon and oxygen. As the way we have arranged our atom in the POSCAR, titanium, C and oxygen, so that way our POSCAR is also arranged. Okay, so now everything is done, and now you can submit this all these input files to your VASP and you will get your result. So that is for normal dynamics. So what if we want to do a dynamics with certain constraint? Suppose I want to fix the coordinates of all the oxygen atom so that I can see how the titanium and carbon atoms are moving with respect to oxygen in a simulation. Okay, so for that what should we do? So we need to fix the coordinate of the oxygen atoms. This is very simple. So how to do that? So it's very simple also. So there we need to do a very simple uh, changes into our POSCAR file. So what is the changes of what will be that change? So the change will be, so here we have written the coordinates of all the atoms with respect to all the atoms along xyz direction. So here simply we have to do what? We need to write this POSCAR file again with certain tags. Like here I have started writing like this. So here I will put one true, true and true. So what is the meaning of this 3t? So one t is along x axis, one t is along y and another is along z. And so this way if I will put true, that means we want the dynamics to be happen. And if we will put false, like this, if if, then it will say that don't move this atom along in, don't move this atom along any of the direction. But if I will put another true over here, that means the atom is fixed along x and y direction, but it can move along z direction. So this is the very simple thing, like very simple way we can arrange our atoms and we can control their motion along any direction. Okay, so, but here what we want to put the true value for all the titanium and carbon. Only we want to put the false value for all the oxygen. So right now I can do this copy and I will paste it. Okay, so this way I am going. And it may take some time, so kindly hold on. So right now I am doing all the editing in this POSCAR file in the insert mode of this BI editor, and also I should count where is that 18th atom of the oxygen. Up to that I will put TTT. After that I will put F. Okay. So from the last I will go now. F, sorry, F and F. Now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and 18. Okay, so now you can see that this last 18 atoms are for are these oxygen atoms, and there we have written this FFF. That means we want to entirely fix the oxygen atoms wherever they are. Rather, we will see the motion of the titanium and carbon atoms with respect to the oxygen atoms. Okay, so now this is fine. Another another thing you need to add over here, so that one is here. You need to go to here after the atom specification. You will add this selective dynamics. Okay, now let's save this. So the entire file is ready now for doing any selective dynamics calculation. Okay, so now you just save this file, and with the same input you can run this simulation, and you will get your a result. And there you can see that the atom that you have made fixed, like the oxygen atoms, they will stay in the same position like as they were in the POSCAR file. They will remain there, but these atoms, this titanium and carbon, they might change their position or something. So that you will get when you will compare your POSCAR with your CONCAT at the end of your simulation. Okay, so this way you need to do, and I hope it will help you in certain way. And this much for today's session, and thank you all.